I'm Carly McAvoy. I just recorded this video for homework 5A and somehow it got deleted, so I'm going to do it again, but you're going to see some writing on the paper because I already did it, trying not to freak out that I'm having to do it twice, but I love math, so how bad can it be? Number 1 is talking about determining whether the value is discrete or continuous random variable or not a random variable at all. So I'm not going to do every one of these, but I will give you a strong hint. If it's countable, then it's discrete. So the number of cars in the parking lot, the number of students doing statistics, those are all discrete. The thing that's continuous is something that you can't count, like a distance or a temperature or a height. The things that you need to have a decimal to answer, those are continuous. And the ones that aren't either are something that's not a number, like what's your favorite pie or something. That's a category, but it's categorical variable, but it's not discrete or continuous. So I'll let you work through that problem on your own. That's 5.2.5, by the way. All right. So how do you decide? This is 5 males with a particular genetic disorder have 1 child. The random variable X is the number of children among the 5 who inherit the genetic disorder. Determine whether the table describes a probability distribution. If it does, find the mean and the standard deviation. How you decide whether it represents is to add up all the probabilities. Those probabilities all have to add up to 1. Just put those into your calculator, add those up. It does add up to 1. They're not going to ask you to find the mean and the standard deviation. It's not. So we need to find the mean and the standard deviation for that. And here's how I'm going to do that. I'm going to go to my data. I'm going to turn my calculator on. Let me clear out the data. Okay, so I go to data and I put in that first row, which is 0, 1, 2, 3, 4, and 5. So I have 0, 1, 2, 3, 4, and 5. Now I'm going to go to my second column and enter the variables that I was given. 0.1804, that's not the variable, that's the probability, sorry, 3685, 0.3010, 0.1229, 0.0251, 0.0021. Alright, so I've just entered all that stuff, and now I'm going to go to second function data, and I'm going to go 1 to the right, hit enter. No, I'm not. I'm going to go 1 down here to variable stats, sorry, hit enter. And I have my L1 is my 0 through 5, so I have data there, and my frequency is the probability, and that I put in that second column. So I want to hit enter so that that's highlighted, and now I'm going to calculate, and it's going to give me the mean, which is rounded to 1 decimal is what they asked for. So to 1 decimal place, the mean is 1.5. And then the standard deviation, notice they don't give you the sample standard deviation, but they do give you the population standard deviation, which is what they asked for here with that lowercase sigma, and that rounds to 1.0. So you just have to put those data into your calculator in that way, and you'll get your the first answer 1.5 and the second answer 1.0 for the mean and the standard deviation there, and that's question 5.2.7. Okay. So this one asks you in the accompanying table, the random variable represents the number of televisions in a household in a certain country. Determine whether or not the table is a probability distribution. If it is a probability distribution, find its mean and standard deviation. Is it? Well, you add up all these values, and we have given the values down here. This is problem 5.2.11, by the way, in case you wanted to know that. But if you add all these up, they add up to 1. That's how you know it's a probability distribution. Okay, so the second part is, if it is a probability distribution, what's its mean? And the second one, what's its standard deviation? Well, we just did that one. So go back and look at the last problem if you don't remember how to do that on your calculator. I give you usually 2 or 3 of the same thing so you can practice so you really get good at your calculator. Here's the answers. The mean is 2.8 and the standard deviation is 1.3. And that one you can check see if you can do it, and then you can always go back and try it again on your own. Chapter 5, Section 2, number 11. Okay. Let the random variable x represent the number of girls in a family with 3 children. Assume the probability of a child being born is 0.35. The table on the right describes the probability of having x number of girls. So remember, the probability of having a girl is actually 0.5, but they changed it to 0.35 so that just give you some more interesting data. The table on the right describes the probability of having x number of girls. Determine whether the table represents a probability distribution. If it does, find the mean and standard deviation. Is it unusual for a family of 3 children to consist of 3 girls? Add these up. If they add up to 1, then it is a probability distribution. Put 0 through 3 in the first column of your data, and these numbers into the second column of your data, and do what we did for the previous problem where I showed you how to use your calculator to determine what the mean and what the standard deviation is. The third part of this, is it unusual for a family with 3 children to have only girls? Well, if you have 3 girls, that means you didn't have any boys, right? So there's 3 girls in this family, and it's 0.04 probability of that happening. If your probability is less than 5%, then we say it's unusual. If it's 5% or more, it's not unusual. 5% is the cutoff, actually. So C, it is probability, yes, what's the question? Yes, it is unusual because the probability is less than or equal to 5%. So if it's less than or equal to, it's unusual. If it's more than 5%, it's not unusual. And there's your number, 5.2.14. Okay, so for number this number 5, there was some data at the bottom that got cut off, so I rewrote it. But the company table describes results from 8 offspring peas. The random variable x represents the number of offspring peas with green pods. Find the probability of getting exactly 7 peas with green pods. Well, here's the probabilities that they gave us. And they want to know what's the probability of getting 7, what's right here in our table. So that's 0.316 given. Find the probability of getting 7 or more peas with green pods. 7 or more means that you could have 7 or you could have 8. So you need to add these two numbers together, 0.316, 0.118. That adds up to 0.434. Which result is relevant for determining whether 7 is an unusually high number of peas with green pods? When you're trying to determine if something is unusual or not, you don't look at the exact value. You look at like 7 or more or 7 or less or that kind of thing. So we want to look at result from part B. If you look at the total number we had, it's more than 5%, which means this part down here asking you if it's unusual, it's not. It's more than 5%, so it's very usual to get that. Okay. All right, so moving on to the next one. Based on data from a car bumper sticker study, when a car is randomly selected, the number of bumper stickers and the corresponding probabilities are shown below. So there was the number of bumper stickers that we're looking at goes from 0 to 9. You know how it goes. Some people never put bumper stickers on their car. Some people can't get enough. So there's possible of any one of those numbers in there. This represents 0 bumper stickers. This one represents 9. Does it describe a probability distribution? You need to add those up and make sure they add up to 1. If they add up to 1, the answer is yes. The answer is yes in this question. Find the mean and the standard deviation. We've already done this. In the L1, you're going to enter 0 through 9. In L2, you're going to enter all this data, and then you're going to do the variable stats, making sure you say your probability, your data is in L1 and your frequencies are in L2, and that's going to give you your mean and your standard deviation. For this particular problem, our mean is 0.5 and our standard deviation is 1.4. So you can use your calculator to get that. Okay, so the next question is use the range rule of thumb to identify the range of values for usual numbers of bumper stickers. The usual values fall between 2 standard deviations below and 2 standard deviations above. So if I take my mean, which is 0.5, and I add 2 times the standard deviation, I add those 2 standard deviations on, that's going to give me my maximum usual value, which is 3.3. If I take my mean and I subtract 2 times the standard deviation, I get my minimum value. Well, actually, this number comes out to be a negative, like negative 2.3 or something. But we can't say that because there's no negative number of bumper stickers. You either have 0 bumper stickers or you have some, right? You don't have negatives. So there's no point in us putting down anything less than just 0. So our maximum is 3.3 and our minimum is 0. Is it unusual for the car to have more than 1 bumper sticker? Well, more than 1 means all of these, right? More than 1, it could be 2 to 9. And if you add all those up and it's more than 5%, then it's not unusual. If it's less than 5%, then it is unusual. And I'll let you explore that possibility on your own. And that's question 5.2.20. Actually, yeah, you can just see it, 5.2.20. That was the end of that one. Okay. There's 20 questions on here, and I am going a little faster. That's not good, but you know, I did it once. So I'm trying to slow down. I don't want to lose you either, but I don't want to repeat showing you the calculator over and over because it just makes the video really long, and you can always go back and use your own calculator. I mean, go back and practice that and watch the video where I showed you how to use your calculator. Okay. Assume that 12 jurors are selected from a population in which 50% of the people are Mexican Americans. The random variable X is the number of Mexican Americans on the jury. So we have 0 people on the jury, that's a 0% chance. 12 Mexican Americans on the jury, that's 0% chance also. But in the middle we have all these different probabilities. If it's actually a probability distribution, all these probabilities should add up to 1. So it is. The probability of exactly 8 Mexican Americans is right here, 0.121. 8 Mexican Americans on the jury, 0.121% chance of that happening. The probability of 8 or fewer, well, 8 or fewer is all of these guys. Could be 0, could be all the way up to 8. And if you add up all those probabilities, you get 0.927. Which is the relevant one. The relevant one is not the one where you just look at one exact value. It's the one that you look at a combined value. So the relevant is the part B there. And does 8 Mexican Americans among 12 jurors suggest the selection process discriminates against Mexican Americans? Do you see how this is way more than 0.05? Since that's more than 0.05, then that's telling us that they're not being discriminated against. They're actually being represented because it's greater than 0.05. If it was less than 0.05 chance of that happening, we would say, whoa, what's going on? Why aren't they representing those people in the population? That's 5.2.22. All right. This one, in a state's pick 3 lottery game, you pay $1.46 to select a sequence of 3 digits from 0 to 9, such as 277. So that tells us that we can repeat numbers because you got 7 again. That's important. If you select the same sequence of 3 digits that are drawn, you win and collect $375.55. Complete parts A through E. How many different selections are possible? When you have 0 through 9, that's 10 different ways to pick a number, and you're picking 3, so you have 10 times 10 times 10, or 10 to the 3rd power, which is 1,000. The first time you draw a number, you have a 1 in 10 chance of getting what they got. Second time, 1 in 10 chance. Third time, 1 in 10 chance. So you have a 1 out of 1,000 chance of actually picking what they picked. That's where we got the 1,000. The next question was, if you win, what is your net profit? Well, you paid, no, that's not what you got, $375 $1.55. You won $375.55, but you paid $1.46 for the ticket. And if you subtract those two numbers, you get $374.09. Okay? Now, expected value, you need to watch the video to me explain what expected value is, but basically it's, what over the long run, if you played this game a bunch of times, what would you expect to make or break on this? Well, you win $374.09 one time out of every 1,000 times you play the game, if things are going in the predicted manner. But 999 times out of 1,000, you would lose everything that you put into it because you normally would not get the three numbers right. So that's negative 1.46. That's your loss because that's what you paid. You lose $1.46 999 out of 1,000 times. If you multiply these two together, you get this number. And then I'm adding because I'm actually saying overall what's going to happen. Sometimes you win, sometimes you lose. So I add those up. And then over here, when I calculate that, I got negative 1.45854. And so my expected value when I add those together is negative $1.08. So that's what my expected value is. Overall, if I played this game 1,000 times, I would expect to lose $1.08 per game. Okay, man, I expect to win once, but most of the time I'm going to lose everything. If you bet $1.46 in a certain game's pick 4 game, the expected value is negative 1.08, again, same as what ours was, which is a better bet, the pick 3 or the pick 4. If your expected value is exactly the same, they're neither one a better bet. They're the same bet. It's a different game, but the same expectation of winning or losing. So A, it's neither better or worse because it's the same. It's the same expected value. Number 9, fill in the blank. A blank random variable has either a finite or a countable number of values. If it's countable, it's discrete. That's the two words you want to put together. Countable is discrete. If a random variable has infinitely many values associated, infinitely many, that's continuous. Continuous means you can't count them. You have to use decimals because there's an infinite amount of choices in there. And if, under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. This represents the rare event rule. So an example of that is, I make the assumption that I'm going to go out golfing and I'm going to get a hole-in-one. And now I go out and I see what the actual probability of that happening, which is 0% in my life, never had one. So the probability is extremely small that that's going to happen. So we would probably assume that my assumption was not correct, that I wasn't really going to get a hole-in-one that day. This is the rare event rule. If you get such a rare probability, such a small probability, below 5%, that means it's probably you've made a bad assumption right from the beginning. That's the rare event rule. Okay. A Gallup poll of 1,236 adults showed that 12% of the respondents believe that it is bad luck to walk under a ladder. Consider the probability that among 30 randomly selected people from 1,236 who were polled, there are at least 2 who have that belief. Given that the subjects surveyed were selected without replacement, the events are not independent. Can the probability be found by using the binomial probability formula? Why or why not? Well, we can use the binomial probability formula even though we did not replace, because when you draw people out of a group of people and you don't replace them, then those, now you've affected, like, okay, there was 12,036 people and now there's only 12,035. But there is a rule that says, well, but if the people you pick are less than 5% of the total population, it's not really going to affect anything because it's still such a small change percentage-wise. So we say that, yeah, it is not, they're not independent, but we can treat them as independent because they were applying that 5% guideline, which says that as long as it's less than 5%, we're not really going to worry about it. If we had 10 people and we selected 2 without replacement, that would be a big difference. but with 1,236, it's not that different. Okay, determine whether the given procedure results in a binomial distribution. You need to look at the notes or the video for the notes about what is a requirements for a binomial distribution. But one thing is we need to have a fixed number of trials. This one randomly selects 100 citizens, so it looks pretty good for that. We need to have independent results, so that picking one person and asking them their nationality doesn't affect the nationality of the next person you ask, so I believe they're independent. We have the same probability of success, but the last part, recording their nationalities, wait a second, for a binomial distribution we need to have just 2 different outcomes, and there's a lot of different outcomes that can be happening if you're asking somebody their nationality. Since we have more than 2 outcomes, it does not suit our needs because it has more than 2 possible outcomes. It is not a binomial distribution. All right, same question. Here we go. 5 cards are selected from a standard 52 card deck without replacement. The number of diamonds selected is recorded. Well, 5 cards are being selected, so we have a fixed number of trials. Good. There's only 2 answers. It's either diamonds or it's not, so there's 2 different outcomes, but they're not independent. They need to be independent for us to be able to use a binomial distribution to represent a binomial experiment. And so we have more, we have not replacing, we go from 51, we don't replace it, now we only have 51 cards in that deck, 52 down to 51, then down to 50, and so forth. Every time we don't replace, we change the sample space so much that this is not okay, because there's not independent trials going on there. We need to make sure that the first trial doesn't affect the next trial, and so forth. So forget about it. Okay, so here, multiple choice questions have 5 possible answers, A, B, C, D, and E, one of which is correct. Assume that you guessed the answers to 3 such questions. Now remember, if you have 5 different choices and you're totally guessing, then 1 out of 5 times you're going to get that right. That is 0.2, right? And 4 out of 5 times you're going to get that wrong, which is 0.8. And I did it before as fractions, but they actually want the decimal, so let's do that. So that the chance that you get it wrong is a 0.8, and then you get it right is 0.2. And when you do that as a decimal, 4/25 comes out to be 0.032. So there's a 0.032 chance that you would get a wrong answer and 2 correct. Okay, 3% of the time. But if you go down to the next part, they say make a list of the different possible arrangements of 2 correct answers. Well, you could have 2 correct at the end, like we just had. That had a 0.032 chance. Or you could have 2 correct answers at the beginning, or you could have a correct followed by a wrong followed by a correct. All those are 2 correct answers, right? So when you look at it that way, it doesn't matter which number you put first, because the commutative property says we can change the order without changing the answer. So 0.8, 0.2, 0.2, those are going to be, when I multiply that, it's going to be all the same. So they all have the same probability. If we look at all those different ways to get 2 exact answers, we just add those up, because there was you could have 2 at the end, 2 at the beginning, 1 at the beginning, 1 at the end, but we have 0.096 chance of getting 2 answers correct. So here's how you do this answer on the calculator. So you go to second function data, and then go to the right to distribution, and go down to binomial PDF, hit enter. And we just have a single question here, is what's the chance of us getting 2 correct on a 3-question test if we're guessing, and every question has 5 choices. Well, the number of trials is 3 because we want 3 different questions. The probability of success is 0.2 because there's 20% chance, 1 in 5 chance that we'll guess correctly. And the number of successes that we're looking for, we want to get 2 answers correct. So we want 2, and so I can calculate that. And that's where I get the 0.096 using the calculator. That's pretty sweet. Alright, so for this one, they have the same thing again, except we want to use the same thing again, except I'm going to solve this again. Now it says that there are 6 trials. So there's 6. It tells us the probability of success is 0.4. 0.4. And it tells us the number of trials, the successes is exactly 3, and so that's 3, and that gives me the 0.276. Now you might notice that this says to use the binomial probabilities table, which I have over here, but you're going to use your calculator. The tables, you know, used to be for people who didn't have calculators available. But if you wanted to use a table for this, you would say, well, there were 3 outcomes. So we go over here to n equals 3. There were 2 successes, that's what we wanted. And then you would slide along until you got to the column that was under 0.2, because we had a 20% chance of success, and that would be 0.096. Oh, that was for the last one. For this one, we were on 6 trials, 40% probability, and 3 successes. So we'd go to 6, 3 successes, and we'd slide over here to 0.4, and we'd see the 0.276. So we could use the table, but that's what they're suggesting, but I would use the calculator. So I'm not going to do this one because you can do that one on your own. 5 trials, probability of success is given, and then the number of successes is exactly 0. That should come out to 0.590. Alright, then number 18 is the same. It's giving you the number of trials, it's giving you the number of successes, and it's giving you the probability of success, and you would plug those numbers into your calculator and you get 0.268. So, and then the same thing again. For number 19, you have 22n, x is 3, p is 0.15, and so we can do the same thing over and over again on our calculator, that binomial PDF, which is pretty sweet. Okay, so let's see. All right. Refer to the accompanying technology display. They have that display at the bottom. They're saying there's 5 trials. Notice when there's 5 trials, there's 6 outcomes. Because it could be out of 5 trials, I could get 0 correct, or 1, 2, 3, 4, or 5 correct. Whatever correct means for us. It could be bad, like how many people actually contract the disease. And we still call it a success because it's what we were looking at, but obviously some successes are bad. The probabilities were obtained by entering the values of n equals 5. Probability is 0.736. And find the probability that at least 4 of the subjects experience headaches. So I'm going to show you how to make you can get the list like this. And you can have a whole list, second function data. Instead of just one, we've been like, oh yeah, we just want that one value. What if we wanted to see all of them like we have here? Then we go to distribution, normal PDF again, but instead of doing single, we want to show the list. So we just go 1 to the right and hit enter. And now it's going to give us, it's not asking X because they're going to show us all the possible X's. But we know that there were n equals 5 trials. The probability of success was 0.736. 0.736. And then I hit enter, and it's going to say, well, what if can we do this? Can we put L1 is going to be this column, and then in the second one, L2 is going to be in this column? And I'm like, yeah, that's fine. I could change it if I wanted, but I'm good with that. So I'm going to hit enter. And you can see over here on the left is the 0 through 5 column. And over here on the right, for 0, it's 0.0013, which is what we got here. For 1, it's 0.0179, and so forth all the way down. So we could get that list on our own. They did it for us, but we don't really need that because we could have done it. But what's the probability at least 4 of the subjects experience headaches? Well, at least 4 means 4 or more. So to get the probability for that, we just add those 2 columns together, right? So that's 0.6033. That's the probability that 4 or more people would have that. Or at least 4 is another way to say it. And then, is it unusual to have excuse me, fewer than 4 subjects experience headache? Well, you just take 1 and you subtract the first bit, and that's how we get the 0.3967. In other words, all this has to add up to 1, here's the people that are 4 or more, and here's the people that are fewer than 4. And so we can look at the number for fewer than 4 and say that's definitely greater than 5%. If it's greater than 5%, then it's not unusual. It's usual for that to happen. So the answer is B. It's not unusual because the probability that fewer of 4 sighted people experience headaches is not unlikely. It's not unlikely because this number is greater than the 5% that we say is the cutoff between unusual and not unusual. All right, second time through it for me was way more fun than the first time. Have a great day, and I'll see you next time.